Welcome to the ETboxMB webinar. I'm Alfonso Lain, and I'm going to introduce you to a comprehensive inspection system based on Eddy Currents for manual inspections. This is an advanced, ultra-portable system with array capacity. It's designed to operate in industrial manufacturing settings or inspection and maintenance tasks. This equipment and its attributes are meant to meet the needs of industries as demanding as aerospace or energy. The system features a comprehensive software tool that's totally adjustable and has user-friendly tactile interfaces, as well as a wide range of pencil, array, or rotating sensors that are particularly designed for conventional and advanced eddy current applications. It's also supplied with the calibration blocks that are necessary to carry out the most common inspections. This way, by purchasing any of the ETboxMB packages, you will have all you need to start working right away. Let me show you the content of the case. Here, we can see the main elements the inspection system is made of. This would be the Eddy Current instrument, and this is the tablet, where the software used for the acquisition and display of data, as well as any necessary settings and operations, is installed. Most of the portable equipment in the market consists of a set with the screen and the electronics all in the same casing. The ETboxMB equipment changes this concept and separates acquisition electronics from the user screen for two main reasons. First, nowadays, we're all very used to managing cell phones or tablets, devices with very vivid color screens and high resolutions. However, most compact equipment in the market has monochrome screens with low resolution. The ETboxMB allows for a next-generation tablet, PC, or any other device that's compatible with Windows that allows for easy updates that follow market trends. The second reason is ergonomics. In compact equipment, the probe is usually connected through a cable. Therefore, if we move along a large component, our range will show the cable length. If we move further, we'll have to keep shifting the whole equipment. However, with the ETboxMB, we can rest the screen somewhere, and we can move freely since the equipment will be attached to our waist, and the probe cable set will move along with us. As we can see, the ETboxMB is small enough to be transported easily to any inspection area, and powerful enough to act as a desktop on laboratories. It weighs around 700 grams, has a robust box that's resistant to falls and watertight, which means it's sealed against liquid splashes and can be operated in the rain, for instance. This is a multi-channel equipment that allows us to acquire up to 4 frequencies for the detection of indications, and whose range goes from 10 Hz to 10 MHz. Let's talk a bit about its front panel. Here we have a number of LED status indicators and a number of connectors. First and foremost is the probe connector, which allows for different types of probes, both from Tecnatom and from third-party manufacturers. Then we have the digital inputs and outputs connector. With this one, we can interact with other elements, take out alarms, work with encoders, etc. There's also a USB port we can use to connect it to the tablet through a cable, although communication is usually done via Wi-Fi. And finally, we have the power supply connection that allows us to work connected to a power supply even while the battery is charging. Let's talk about the battery. The equipment has a range of up to 8 hours during the use of a conventional probe. This allows for great flexibility since a whole inspection journey can generally be completed. On the other hand, the equipment usually comes with a rugged tablet, although any device that comes with Windows 10, will be compatible with the system. The fact that the user interface runs on a tablet allows, on the one hand, for user-friendly interaction via the touchscreen, and on the other hand, for the use of tools, such as picture taking with the photo cameras included in the tablet, report generation, or even cloud file management if we connect the tablet to the internet. This new equipment deserved the development of new probes. That is why, for this system, different probes with new features have been developed. Like, for example, configurable buttons, lighting LED, or even automatic detection thanks to the inspection system. Therefore, the ETboxMB equipment developed by Tecnatom and its whole ecosystem is perfect for eddy current tests, as it allows for the fulfillment of all requested tasks in a reliable, easy way, and with a single instrument. Now, we're going to do a general description of the ETboxMB software. To do so, as we can see on the screen, we can find our icon to run the application on the first screen. On this first screen, we can see all the equipment and instruments that are within our reach. It's found the ETboxMB 1006, so we could connect to it now if we wanted. If we were connected to the tablet through a USB cable, this screen wouldn't show up. Instead, the next one would appear. We're connecting via Wi-Fi. Okay, so this is the main screen of the application. Okay. On this screen, we can see that we have 4 accesses to different application: conductivity thickness, eddy current, rotating, and array. In order to describe a bit of the different menus and submenus, I will use Eddy Current 1 as an example. Alright, here we see the main view, which is what we see when we start working with the equipment. Then we can see on top of the screen, in a small white font, some of the general information. Starting from the left, we have the tablet information, which shows the remaining battery, 66% in this case, the application we're using, which is Eddy Current, the date and time. Next, we have information about the equipment, the instrument we're connected to, the 1006, and the battery power left over. We're charged up to just about 100%. Here we have the Wi-Fi icon, which is the connection mode between the instrument and the tablet. Then we can find, at the bottom, a toolbar with some purple icons that we can see. There's also the arrow symbol to go back to the main screen, a lock symbol that locks the screen. In order to deactivate touch input and make sure no parameters are changed accidentally while we work or carry out some inspection, there's another button to make a screen capture of what we're seeing anytime. A shortcut to take pictures with the front and back camera of the tablet. The General Settings button. Here, we have access to the language settings, to choose the appearance or the color we want for our equipment, as well as the size of the buffer we're going to work with. The next button we can see minimizes the application so that we can get access to any other application in the operating system or even create reports. We can then go back, and here's the off button. On the layout, we can see on top of the screen that there are 4 buttons that belong to each application. These are the most commonly used when carrying out an inspection, since they have the basic parameters of the test that's being done. In this case, as we're talking about eddy currents, we can manipulate the offset, the gain or the phase, do a hardware null to center the signal, or pause the acquisition. As we see, another orange tag appears that indicates the acquisition is stopped. as we start acquiring again, and it says the acquisition has resumed. And then there's the delete button, which deletes all the buffer data in case we want to start from scratch. As for the menus, we can find on the right and the left side, we see the main menu is the right one, with several tabs that we can open, so a series of submenus drop down by the left. Quite often, the left menu does not include all the options we would find in said submenu, which is why there's the possibility to move the different pages to have access to each one of them. The first one, the technical one, grants access to set up all the eddy current parameters you can need, such as the gain, the attenuation to the probe feed, or the offset of the signal you're working with. Here we have gain, or even the control of the filters. Then we have an application that's very important called alarms. This support tool is really useful for operators who are carrying out inspections, as different thresholds can be defined with it, so that when the signal goes through them, it creates a response in the form of alarm, whether it's a sound, a light signal, or both. This allows operators to focus on the area to be inspected and on the manipulation of the probe, while being able to look away from the screen, since as soon as an indication appears, some of the pre-configured alarms will go off. This application is very flexible and completely customizable depending on the needs of our inspection and the nature of our signals. We can also configure it so that the instrument creates an alarm and generates an exit through its digital output. This gives us endless possibilities. The next tab we'll see each of the applications along with an example of an alarm so we can see how they work. The next tab is Display. This one obviously grants us access to the graphic settings and the way we want to visualize the signals. We can choose Lisa Use with 2 strip charts. Anyways, different ways to see it. Then we can choose whether or not we want a grid that divides the whole screen, as well as the size of said grid, or if we want the lines to be horizontal or vertical. Next, we have the Advanced tab. This gives you access to the parameters of the instrument. This gives you access to the parameters that are less common on conventional inspections. We can configure the encoders. We can configure the analog inputs and outputs, and the digital inputs and outputs we have connected. And finally, we have the Utilities and Reports tab that we will comment more in depth in another video. With these, we could do a different type of... We could set things up and save reports. This is just a general overview of the software. And now, we're going to explain a series of descriptions and demonstrations to show some of the applications that we've got. In applications for industries such as aeronautics, the need to measure conductivity changes is very common. For example, changes produced by overheating on the brakes over the wheels. Similarly, the thickness of paint layers or coatings with materials that are non-conductive of metallic components are also measured. The ETboxMB equipment allows to do such measurements independently or as a whole. In different working modes, as we're going to see, this tool guides the operator with the easiest graphic interface. Let's see an example using this probe, especially developed to measure conductivities. As we can see, the probe has a small LED that lights up with the alarm that we can set up, and it's a probe that works at 60 kHz. For this demonstration, we also have 2 conductivity measuring blocks. In this case, these are 2 aluminum blocks that have their own certificate. These blocks are manufactured and certified by Tecnatom to calibrate the conductivity test. On the other hand, for the thickness test, we have several certified patterns with different thicknesses. In this case, we've got gauges that go from 53.7 to 512.8 microns, depending on the range we want to work with, as we will need different gauges to work with different thicknesses. Moving on, let's start our conductivity thickness application. It has identified directly the probe we have connected. Okay, this is the main screen that, as you can see, is a bit different to the ones we've seen before, because on this screen, we set up the calibration we're going to do. On this menu, we can choose between work modes. If we want to measure just the conductivity, just the thickness, or do a mixed measurement of both of them. We can also choose the units in which we want our measurements to appear. We can go between megasiemens per meter or IACs, or between microns and inches. In this case, we're going to work with the international system. We can also choose the units in which our temperature will appear, either Celsius degrees or Fahrenheit degrees. It's important to introduce the test temperature since, under that, the algorithms are going to work with it to obtain better accuracy. Okay, so once we introduce the conductivity and thickness values of the patterns we're going to use to calibrate, in this case, I had already pre-charged them, but their tactile insertion is very easy. One is 26.96 and the other 46.38. And for the thickness measurement, we're going to do it between a zero gauge, that is, with no gauge, and use a medium thickness of 129.1 micron. Once we have everything ready, we click on Next, and the software is going to guide us directly through the steps we need to follow. In this case, we put the probe on the air. To get a reference, it tells us with the lowest conductivity and lowest thickness pattern. We hit Next, lower conductivity and higher thickness, Next, and higher conductivity and higher thickness, and higher conductivity and higher thickness. Okay, so this is how easily we've done a calibration for our conductivity and thickness test. Now we can see on the screen some menus and submenus that look more familiar to us. In the upper middle section of the screen, we can see the conductivity measure, and in the lower part, the thickness measure. On the Technical tab, we find a description of a series of parameters we can choose. That would be the acquisition mode, which is in this case automatic, and the software identifies if the probe is on the air or if it's laid on the material. When the measurement is fixed, it goes blue. If we set it to continuous, this is measured non-stop. It refreshes our measurements constantly. If we change thickness, we can see both are visible all the time. Finally, if we have set it to manual, in this case we have to do a screenshot of the measurement ourselves. Every time we hit screenshot, it takes a screenshot. One of the options that's activated right now, which we can turn on or off, is one to calculate the average of measurements. We have up to 8 fields. This application is really useful when we have to inspect a large component and we take a sample in which, according to our procedure, we have to measure several times. That way, we capture the measurements, then another, and it calculates the average directly in order to understand what the conductivity or the thickness of that component is. On the other side, we also have an alarm set up. In this case, they've already activated, and we can see that the alarms go off when they're out of range. We also have the opportunity to change the display, but here we can only change between conductivity, thickness, or see both measurements. We have the chance to generate reports as well, but we'll see that later. This would be a general example of how to perform a combined inspection of conductivity and thickness. It should be noted that all of the algorithms used that back up the calculations of these tests have been subjected to thorough accuracy tests in order to ensure they are compliant with the most common demanding guidelines. To detect and set apart open cracks that are superficial or subsuperficial in inspections of components manufactured with conductive materials such as landing wheels, fuselage, or pipes, it's necessary to do the test via eddy currents to different frequencies. In order to do that, the ETboxMB equipment can be set up really quickly and work with up to 4 frequencies simultaneously. We can even modify the test parameters to meet the inspector's needs. I'm going to do a demo where, with a basic setup, we'll do a calibration and acquisition of this calibration block with 3 notches. To do so, we're going to use this pencil probe. It's a probe developed by Tecnatom, whose work range goes from 500 to 1000 kilohertz. It has a push button, so in this case, we've set it up so that we can use a long push to turn on the LEDs and the short push to do a hardware null. It also has a small LED that lights up when we have configured our alarms. We're going to start the Eddy Current application. It identifies our probe right away. Okay, so in this case, we've already seen the distribution of the screen. Let's configure the display the way we want it to perform our inspection. For that, we'll go to the Display menu where a sub-menu spreads out. We have a Lisa Juice open, and we're going to use Strip Chart with Alicia Juice. Once we have that part configured, we can also see there are several other options among which we can choose. The equipment is acquiring, and it's important to take into account that we can turn the persistence mode on or we can turn the persistence mode off. That way, we see that if it's turned off, the whole signal that's acquiring until the buffer is full accumulates on the screen. However, if we turn it on, what we see is that it only represents the 2 seconds that we have configured. We're going to leave it that way to work. We go back to the technical menu and we start calibrating. The first step is to focus our signal in the impedance plane. To do so, we will do a hardware null, and as we can see, it's running now. Our signal is focused both in the horizontal and in the vertical components. To perform our calibration, we acquire the liftoff and the 3 notches. We make several passes. Okay, now we stop our acquisition. As you can see, we've got a timeline where we can see the signal that is accumulated in the buffer, that is, from the latest 20 seconds. And with this window, we can choose whether we want to see more or less data on the strip charts. We're going to close the window and choose, well, we're seeing this stage. The first thing we have to do is to change the phase. We can also see the phase in this menu, which is 0 degrees in this case. And we can rotate the signal via the touchscreen in order to assign the phase we need to it. As we're seeing, we put the liftoff signal horizontally, which is a common way to calibrate the phase. Now we calibrate gain. In order to do that, we have to search the area where we have acquired the notches. Right now, we have a very low gain. On this screen, we can manipulate the gain so that we can change both components at the same time. We can put it directly on screen or even through the touchscreen. In this case, let's give both components a bit more amplitude so they have enough entity. Alright, once our equipment is configured and calibrated, we can see some other features of this application. Both of them are related to display. We can also see we have two tags with the measurements, in this case phase volts and peak to peak. These two measurements that appear on the sides of the tag with the channel we're working on are configurable. I mean, we can choose volts, peak to peak, phase, volts on the horizontal, or on the vertical. Okay, the whole screen can be configured. Once we've seen that, we can talk about the tag that's on the alarm section. We have up to 4 alarms ready to be set up. In this case, they're deactivated, but we're going to activate them. Okay, we have several alarm modes. I have activated one that's the polar one, but you can also use the one that's thresholds, for example, horizontal, rectangular, circular, or polar thresholds. All of them are configurable via the touchscreen. We can enlarge them, reduce them, depending on the area of the impedance plane that we're interested in working with. For this example, I have chosen a polar pattern, and we're kind of sure that the signal amplitude of our biggest entity notch is going to reach this point. Okay, well, we're all set. Let's acquire the notches. We see that the first two do not have enough entity, and the last one, as it already breaks the alarm that we have prepared, the LED lights up and we have the luminous signal. Every time we pass through it, we would be triggering the alarm. And this would be an example of how to work with alarms. Likewise, if we need to work with several frequencies, well, it would be as simple as configuring and activating one more channel. So we can see that the screen is divided, and we have available the same frequencies that we had for a single channel for both. If there were 3 or 4, it would be exactly the same. Thus, as this is the basic Eddy Current application, it is still enough for a bunch of inspection applications. In addition, it has the possibility of using a wide range of different types of probes to adapt to the most complex geometries with very low costs. Now, we are going to talk about another need that's covered by the ETboxMB system. This is actually the detection of cracks inside holes or bores. This type of inspection has the peculiarity of needing a probe that rotates inside the housings, since we need to check the walls of these. We use this type of probe for this. As you can see, the probe has a body inside, which is the motor, as well as a rod with a coil. In this case, it's prepared to do an inspection of bores with diameters between 8 and 9 millimeters. But we could change it for a different one depending on whether we need a larger or smaller diameter. We can also see that the probe has an LED that lights up when an alarm goes off, and a switch to activate and deactivate the rotation. In this demonstration, we will make use of this calibration block that has 2 holes, one of them with indications and the other with a crack, as we can see in this image. Let's proceed with the rotary rotation application. We see that it loads. It has identified the probe. And we can access the application. This application is very similar to the conventional Eddy Current application. We can see we have the main menu with technical, alarm, display, and the rest of the tabs. Then we have submenu on the left. We also have the same buttons at the top to modify the offset, gain, phase, do a hardware null, control the acquisition, and clear the buffer. Knowing this, I am going to focus on the parameters that differ from the other application. First, when we do this inspection, we must always check the rotation speed at which we want to make the acquisition. Right now, it's set at 1,800 revolutions per minute. We see we can change it and set. Let's set, for example, 1,500. And now we can pull off the probe sleeve to make an acquisition. Like all current calibrations, in the first place, we're going to get in the safe zone. We're going to do a hardware null. Okay, and once we have centered the signal, we can acquire the board that has the notch in it. This way, we can see the notch. We're going to do a calibration of the phase. There. And, well, the gain, in this case, is correct, so we're not going to manipulate it. Once we have the calibrated signal, I want to mention some of the configurations that we must take into account with this kind of probe, which are the activation of the filters, high pass and low pass. In this case, we can see we activate the acquisition to be able to manipulate the filters. Well, here we have the high pass filter. This filter is essential because if we turn it off, an artifact is introduced into the signal that is the result of the rotation of the probe inside the borehole. This generates disturbance in the signal. And as we can see, we won't be able to do anything with it. Once we activate it, the signal becomes way smoother. On the other hand, we also have the low pass filter, which, when we turn it off, we can see that a noise comes from the motor rotation. It's an electrical noise, and once we activate it, it's filtered. We can lower it a bit. We can lower it a little bit more. And here we see it. We go into the default and we can see it. Two other buttons I want to explain to you are, first, the sync filter speed, which right now is disabled. If we activate it, what we get is that once we change the rotation speed, both the high pass filter and the low pass filter are automatically calculated following some charts contained in the instrument. And we are going to see, well, we're going to connect the Shape 6 button, with which we can get the shape of the signal to be one that operators are generally used to. It's a signal with a crack that makes a 6 shape. This would be like if you look at the absolute, and if we disable, we have the classic 8 of eddy currents. On the other hand, this application has some differences regarding the graphical representation, since when we turn, we have the same modes we have seen. We activate or deactivate the cursors, we can work with persistence mode, switched on, or off, and then we have phase sync persistence mode. This is very useful. It's also the one we have activated right now, because with it, we can see only one lap. And once we are acquiring our signal, we see one lap, and we can configure it and tell it, hey, the crack signal I'm seeing, I want to. Now it had turned a little bit. You can put it in place. For example, here you say, let's put it at 0 degrees. And whenever we find a crack at that position, we know it's going to show up there. That would be it with this value. If we weren't working in persistence mode, we would just be in time mode. In that case, we would be looking at the whole signal continuously. Here we're seeing it for 1 second. We can set it to 5 seconds, and it would accumulate the 5-second signal. Also, within the Display tab, we see that we can configure the measurements that appear in our top toolbar. In this case, there are two differences with the one we had in eddy currents. One of them is that we can put revolutions per minute, and the other is that we can put the VPOs. Here, it's giving us the position that would have the signal of greater entity on the screen relative to 360 degrees. As we have been able to calibrate with phase sync and with a notch, we have been able to tell where the notch was. Here we can measure, and right away, the peak of greater amplitude tells us in what position of the rotation it is. On the other hand, in RPM, if we check the revolutions that are configured when the probe stops rotating, it turns red and an alarm goes off saying, "Be careful, we are having a problem in the rotation. The control term is not being met." Another difference that we find is that right now it would be activated. We have a C-scan view available. With this C-scan view, we can look at the timeline and the 0 to 360 degree line. There we would be looking at the notch. If we change, okay, well, we go back to a view, to our normal view with phase sync and 0. Okay, now we have it, and it goes on. We change, you see, now we've already changed the position, the notch position calibration, and it appears in another situation. In addition to the differences we have seen, if we configure the normal view, the alarm screen is activated and, well, okay, we have one configured that would work in a similar way to what we have seen with eddy currents. Every time the signal gets to the alarm, it goes off. However, when we don't have any cracks, nothing happens. And in such a simple way, we can proceed to inspect all the holes in a component before it's assembled and riveted. Even more complicated applications, where there are several layers to be discriminated, and where the access is also a small drill. Nowadays, one of the most important parameters is to perform inspections in the shortest possible time without compromising the quality of the test. One of the eddy current applications with the greatest impact on this aspect is the array technology. Thanks to this technology, we can perform faster acquisitions by covering larger surfaces in a single pass. Furthermore, depending on the number of windings and the distribution, we can play with different operating modes according to the type and direction of the indications we're looking for. For this demonstration, we have an array probe with 16 windings, although in addition, the probe has a push button that we can configure to make hardware null and the balancing of the signal. Besides, I'm going to make use of this calibration block that has 3 notches with different depths. To do this, we will go to our ETboxMB application and run the array application. It has identified the probe right away. We see it's a 16x1 absolute probe, and it loads a configuration for these kinds of probes. Alright, so once in the application, we see the distribution is very similar to that of eddy current and rotary. We have a main menu on the right, the submenus on the left, the work buttons at the top, and some more indicators that we will explain later. Note that the configuration of the different displays we see on the screen is fixed, and we only have the option to switch the C-scan view with the 3D view of the signal. Plus, Here we have a Lisa juice and the time bar where we will see all the signal, where all the signal that fits in the buffer is accumulated. Okay, first of all, we're going to perform a calibration. Unlike the eddy current test, this calibration has 3 steps, one more than this one. We need to do the hardware null to bring our signal to the middle of the screen. We have to do a calibration to equalize all the probes. And then we'll do the typical gain and phase calibration. We choose the area of the block with no defect and do hardware null. Okay, once we acquire the hardware null, we can pause and we can see how the signal has been acquired, then reacquire. Well, I don't have a defect through which all the signals pass. We're using the liftoff signal as a step and thus be able to equalize all the signals. We're going to lower the gain so that this signal is not saturated. So I put 10 and 10. Okay. Now we have the whole signal on screen. I can pause. Okay. What we're going to see, what we want is for these little deviations that the signal has to be totally eliminated. We go to the signal, to the stage, we calibrate, and our signal is totally flat now. If we go back to the acquisition, balance, and we are now ready to acquire the notches with which we'll do the phase and amplitude calibration. Well, we can already see that they are there. We pause the acquisition. Okay, I'm going to position it so that we can see it a bit better. Well, as we're seeing both in the C-scan and in the 3D, being a color representation, we have our color calibration here in case we want to maximize the defaults. And now, we go and click on Gain. All right, before the gain, we must put in the phase we want. In this case, it's the stage we're seeing. We are going to place the liftoff in the horizontal. Now, we acquire the liftoff. We pause. We see it on the screen, and we rotate it, there. We can also choose that what we see in the C-scan as well as in the 3D is the vertical or the horizontal component. Depending on the calibration we're doing, we're working with the vertical component. Some of the differences we see on screen when we're acquiring are that in this case, 2 squares appear with new information that belongs to an array. 6 would be, 1 would be for the position, that is, the coil which we see the signal, and the other, the position on the x-axis. All of these parameters are configurable. If we go to Display, we can choose which ones we want to see. It's important to note that The measurement we see, in this case of volts, either gain or phase, is always of the maximum amplitude signal, so that if we want to measure a defect that is not the largest, we must isolate it on the screen, as we're doing here. Okay. As we've seen, the ETbox allows us to make acquisitions quickly, both for its easy configuration and for its versatility in displaying the indications with 3D representations. A tool that, along with some of the flexible or adaptable array probe models, guarantees the success of many inspections. To conclude, let's see some tools that are common to the 4 ETboxMB software applications. These are, as we see on the screen, the ones we find in the Utilities and Reports tabs. If we select the Utilities tab, we see that we have the possibility to save data, save configuration, load configuration, and view our system information. This is the screen we see when we run it. We can also look here to see the probe that's connected, the software version, and the setup of the current instrument. If, for instance, we're performing an inspection and we need to save the signal we have acquired, it would be as simple as hitting Save Data. Create a folder and call it Web. Then create a file name that we will call File. That way we would already see all the saved data we have on the screen. Then, if we have to recover them, we would just have to click on Load Data. We can also save the configuration. Similarly, it asks us to type the name of the configuration we want to save, and this way, if another operator or some other time we return there and we want to load the same configuration or review the data, we would already have them available. A very relevant and very useful application when carrying out inspections is the report generation. For this, we have 2 tools. One of them is the screen capture tool. If we've acquired an indication that we consider important, for some reason we want to save what we are seeing, and if we want to save what we're seeing, press Save, and it saves the image we're looking at. And if, for example, we are looking at an indication and we want to take an actual picture of said area, it's as simple as opening the camera application. In this case, I'm going to take a picture of what I have to calibrate. We take it, and it's available. That way, if we go to Reports, we have both the screenshots and the image we have acquired. Besides, by clicking on Add Configuration, an image would be saved with all the configuration data we have used to perform that inspection. And in this way, if we were to click on Generate Report, it generates a Word file that we can see. It generates a Word file that has been created in the folder. This Word document grabs a template, and as we can see, let's enlarge it. Well, in this case, we could fill in all the client's data. It's an example. And it has already inserted, right away, the images of the acquired screen, as well as the photo or the configuration of the equipment. We go back to the application. Okay, as we have saved it before, we will see we have the file we saved, and that we can visualize, reevaluate, and study it. As you can see, these applications complete a software tool really designed to make field inspection tasks as easy as possible. It gives us the chance to have a fluid workflow, from the purest technical operations to all of those documentation and processes that require non-destructive testing procedures. And that's a wrap for the ETboxMB webinar. Throughout this series of explanations and demonstrations, I've tried to show you all the capabilities this powerful inspection equipment can offer. For more details, and if you want to learn more about this and other non-destructive testing equipment, you can check out our website and contact us. Thank you very much, and see you in the next video.